entirely from computer science or specifically from programming language theory, functional programming language semantics. What is it about? Even before, there are a number of names on the slide, and this is essentially because there are two papers I'm referring to plus some extra observations. One is a FOSAX 2016 paper of Soichiro Fujii, Shin-ya Katsumata and Paul-André Melliès, and then there is an ICT paper also this year by this group, the second line. So what is this? So in programming languages, functional programming specifically, and denotation and semantics, we tend to organize computations with side effects, like computation with exception, state, nondeterminism, interactive I/O with monads, and then there are related concepts from pedigree that you also use to deal with different specific notions of computations that aren't purely functional, like idioms, which is a good name for lax monoidal functors. Comonads, arrows, relative monads. And in this game, it's often useful to track kind of what I'd like to intuitively call the degree of effectfulness, how much impurity there is, somehow to quantify the impurity. So for example, for ensuring safety, so suppose you're given some resource bounds within which you have to operate, and then you'd like to make sure that you honor the given resource bounds. Or maybe if you know that the effect isn't bigger than so, then you can do some optimization in compiling the program. So swap out the program names for something simpler. That's another typical example. So this is what we'd like to use for what I here call grading. Some other people use different words. So people have been talking about parameterized monads, and there are some other words which I've forgotten. But in terms of computer science or PL literature, this is essentially revisiting the old idea of type and defect systems, tangible law, etc., which was exactly about monads were not there, but it was somehow about quantifying, in some sense, effects. But also some old work by Phil Water and Peter Thiemann, where they talked about marriage of monads and defects, and something was done on the level of syntactic type systems, but the semantics was not quite settled. And that then goes with the effect inference and all that. The idea is you've got a piece of code you'd like to give the best, the tightest over approximation of the effect that is there. Typically to the way that you do in static program analysis. So you're maybe after a kind of a modification of a monadic meta language like this. So usually we talk about types of values, like this A could be here, and then you would say the type T of A, monad applied to a type or a set, is the type of effectful computations over the given type. And if T is a term, red T is a term, and the semantic idea behind this is you just apply the unit of the monad. But now there is, the monad is graded, and this I is actually will be a unit, the unit of a monoid, and basically tells you there was no effect. This was the trivial effect here. And when you compose two effectful computations, if you've got this kind of a lead binding here or a generalized case, so you deal with the sequential composition of two effectful programs, you'd expect that there is some operation that tells you what the aggregate effect is if you know what the effects of the constituent parts were. Which will be very soon be the multiplication of a monad. That's it. And then maybe there is some idea that you don't quantify precisely, but you over or under approximate. So there is some partial order. Right? That's all there is, right? On the level of intuitions. But now we have to sort this out. So I'll give you a long unpacked definition, and I just condense it into one line, which is a categorical triviality. But I first start with examples. So let me. Okay. This is going to be the outline. I'll concentrate on graded monads and then look at variations. One of which will be graded monads of monoids, graded distributive laws, graded comonads. And then I'd like to do graded monads first, but starting slowly with examples. So let me jump over the definition. This is the first one. So you talk about, in function programming, you talk about exceptions using this monad T, which is T of x equals 1 plus x. So a computation is either well, a distinguished element, think of a failure, or it's a proper value. And now I'd like to say, let me differentiate between sort of three different grades. Either I have a pure computation, or I have a definitely failed computation, or I have a computation which maybe fails, which is the general case. And then there is a natural partial order you could put on these things, right? And you would say, well, the pure computations would live here. Sounds reasonable. Then you start to think, what if I have a pure computation followed by one that fails? Well, the total result is a failure, right? If you follow a fail by maybe fail, maybe this is maybe fail. Maybe this is still fail, right? But if you follow pure by maybe fail, this is maybe fail. So you get this small multiplication table. This is a monad. It's actually an ordered monad. Multiplication is monotone. And now, what is a graded monad? Is a monad could have parameterized in these grades, will make it precise. So in the pure case, you don't really need all of x plus 1, you just need x. In the case of failure, you don't need x plus 1 either. You live in a smaller set, which is 1. And the general case is x plus 1. And you can, you have these coercions. So if you know that one grade is smaller than another, then you can have some corresponding injections. So this is the most trivial example that you can think of. Let's make it a bit more interesting, and let's make everything official. So I want to talk about readable, writable state. I want to be able to read some imperative state, and I'd like to be able to override state. So there is a state space S, and normally in this functional programming story you talk about this state monad that you actually get from the adjunction between product and exponential, S arrows S times X. So this is the general case. You read, you write, and the stateful computation of a value in the end is nothing else than the dependence of a value on an initial state and the dependence of the final state on the given initial state. But there are special cases. Maybe you know that your effectful computation only wrote, or only read, or did neither. And actually about writing you have to be a bit more precise. So I've got two different grades here for write only. Write only means you only write, you don't read. And what I call here write only plus means you only write, but you write at least once. And this is the order. And there is the corresponding multiplication table. And maybe you'd like to complain about one point, which is how is it that if I write at least once, and I follow by something that reads only, that I can grade this with write at least once. But it makes sense. Because if you write only and you write at least once in a first computation in a sequence, and then you read, you're not reading what was originally there. You're reading something that definitely was a state that already been written over by something that was actually under your control. So there are several ways that you could explain this to yourself. One is to look at the Laurier theory of the state monad and see what the normal forms are, and see in the case of write only plus, I know that there is at least one proper write there, and if this is followed by the read, write followed by a read is just a write, because you know the result of the read. But the other is also to think of these types as subsets of this type, satisfying certain properties. Like here, for example, I'm talking about functions of this type, where I know that the first component returned is just the argument, right? You haven't touched anything. You don't write, so you know that the final state is going to be the initial state. And then there are similar characterizations, extensional characterizations of these sort of subsets of the function space. Okay, and maybe one more example. So I want to talk about the free monad, and we want to grade it. Right? So there are several ways you could do it. So one could be the following. So you're given an alphabet, sigma. So I'm talking about the monad T, which is T of x is just sigma times x. sigma star times x. Sigma star is a free monad. And one idea could be to use natural numbers with a natural order of them, 0 and plus, the additive structure, and you say, well, at grade n, all you're allowed to write is to write words not longer than n. But of course, you could be cooler, you could be way more precise. So in principle, you could use languages as grades, and then the idea is you can only write words drawn from the given language. Set inclusion is then the partial order of language inclusion. The unit is the language consisting of only the empty word, and the multiplication is concatenation of languages, which is just given by concatenation of words drawn from the languages. And then the graded monad, t of x at grade L is just L times x. So you're only allowed to write words from a given language. Okay, so what is this? It is the following thing. So the situation in which we are is this. You're given a monoid, which I use multiplicative notation, and then a graded monad on a given category is the following thing. So for any grade, you have an endofunctor. There is a natural transformation between identity and t at I, at the unit of the monoid. And for any two grades, multiplication for these two grades takes you from t of f after t of e after t of f to t of e times f. So aggregating the effects. And you will require the obvious generalization of the monad laws. You start writing down what they have to be, and you discover that you cannot do with less than a monoid for grades, because you see, for you to even write down the diagrams, you see that you need the left unital law, the right unital law, and the associativity law of a monoid. So it cannot be just a set with an arbitrary binary operation, and the distinguished element really has to be. If we think what this is, well, all this unpacked definition is really unnecessary. A monad is nothing but a monoid in the category of endofunctors, and here we've got a very slight generalization. So a graded monad on C is nothing but a lax monoidal functor from the monoid, not seen as a one-object category, but seen as a discrete monoidal category with actually carrier many objects and no maps of their identities. From there to the monoidal category of endofunctors with the obvious composition, monoidal structure. That's it. And then a slight generalization is you don't start with a monoid, but you start with a comonoid, a partially ordered monoid. And if you unpack the definitions, then of course you see things. You see that you must be able to, upgrade a computation, and somehow upgrading should be coherent. So you upgrade from E to E prime, and then further from E prime to E double prime. Of course, that's the same as to use the transitivity and do one single upgrade. And then moreover, this diagram has to hold. But again, in some sense, this is all unnecessary, because all that we have is a graded monad on a comonoid. Is again a lax monoidal functor, except that this time I don't start off with a discrete category, but with a thin monoidal category. And obviously you could also grade with a general monoidal category, but there are maybe not so many interesting examples directly coming from my applications, but that's certainly possible. Okay, that's the game. So let's try to do a few things. We could try to see if we can sort of generalize standard monad theory. What about Kleisli? What about Eilenberg-Moore? What about resolutions? These kind of things. You can do all this. What's a Kleisli category? I'll first tell you what it is, but then motivate it, because it's going to be the initial resolution, etc. So you're given a comonoid, and you're given a graded monad where you use this comonoid. An object in the Kleisli category is a pair of a grade and an object of the base category. And the map is a bit complicated, so a map between two such pairs is given also by an element of E. It has to satisfy this inequality. And then a map from, looks like an ordinary Kleisli map, but then you use T at F. And the way to think now about these things, sort of from the programming intuition, is you're talking about maps from x to y, so computation sending x's to y's. Think of this E as the effect accumulated before you are starting to apply the map we're talking about this, and D prime is the post, the aggregate effect afterward. And F is kind of the difference, or what fits in between. Actually, yeah, since I use multiplicative notation more like a ratio. But that's the idea. And it's a triple like this. And the only thing you have to do is you also have to take a small quotient, because there could be several F's that fit in here. So if F is smaller than F prime, then maybe you want to identify F and F prime. This you can do if this equation held, and inequation held, and if you then decompose with this, and then also you can expand. If there is K here and the map here is obtained by K and upgrade. Yeah, this looks bureaucratic, but comes out very naturally if you think about generalities here. The Eilenberg Moore is also not tricky to see what it is. So an object, let's call them algebras. What is it? So here we had pairs as object. Now it's going to be carriers are not going to be just objects of the underlying category, but they are going to be functions from grades. So for any grade, I have an object capital A E. Then I can mediate between A E and A E prime if A is smaller than E prime. And then there is the structure map. Parameters in any grades E and F. So from E of E applied to A of F, you can get to A of E times F. And there is an obvious notion of an algebra map. And you obviously get what you want. For example, that multiplication gives you the three algebras. So what about splitting a monad into an adjunction? So here, a graded monad. So given a graded monad T, a particular resolution is given by a category D, and a pair of adjoint functors between C and D, but a little more. So in general, there will be a strict monoidal functor between the comonoid and the monoidal category of end of functors, but that's wrong. These should be D's here. And then you say, well, T of E is nothing else than R after A of E after L. So it's a generalization of the usual story. And of course, you have appropriate conditions on the unit and multiplication of the monad as well. And you get standard things like twice the category is the initial resolution, and then more category is the final resolution. So let's play some more such games, and you see that you can apply the same pattern to other situations that we have in programming language semantics. I've spoken for 20 minutes, is that correct?
Yes, we should go until 3-ish.
My next game is this. This is something that is called monad plus in the Haskell programming language. But let's leave this aside. I just call this graded monads of monoids. So it's a specialization of monads that I call monads of monoids, and then we are going to grade them. So what's the story? Maybe you first look here. So now I'm in a situation where the base category cannot be entirely without structures. So say it's Cartesian, although monoidal will also do. So there are finite products. And I require the following thing. So in the ungraded case, I would require a map, a natural transformation from constant 1 to t, and from t pointwise times t to t. And these kind of things you use to model non-determinism. So typically, so this here would correspond to arriving at a situation where you're faced with having to choose between with 0 options. So it's a kind of a suicidal situation. And this corresponds here to binary choice, right? So you've got t of x, you've got another t of x, and you want to have canonically an element of t of x again. Now we want to grade this. I'm going to use a double monoid structure on the given set E of grades. So we had this multiplicative structure which was for composition of computations. Now for choice we had another monoid structure for which I use additive notation. So this MZ comes from the Haskell language, M0. M is what is in Haskell is M+. But it doesn't matter, it's just some names I invented. So here I use grade 0, here I use E plus F. And you see that there is the same sort of preservation of monoidal structure going on already, right? Previously we sent the multiplicative monoidal structure on E to the composition monoidal structure on the category of endofunctors. Here the product structure on the category of endofunctors, sorry, here the additive structure of the monoid gets sent over to the product monoidal structure on the category of endofunctors, and laxly, because these guys are not isomorphism, but they're really natural transformations in the appropriate direction. And you might wonder how the two monoid structures have to interact. The first guess would perhaps be semirings, but that's actually a bit too much for most examples. So really what you need is these right near semirings. So this means that times distributes over the additive structure only from the right, and also then commutativity of addition is not required. And again, one way to arrive at this is simply to try to write down the kind of laws you'd like. Of course, you'll discover that the additive structure has to be a mono structure, but also you see that you need distributivity from the right. And here what plays into the picture is, of course, that the category of endofunctors itself has a right near semiring structure. So I can distribute composition over product from the right. And this is an isomorphism. And I cannot actually from the left, at least not as an isomorphism. I could have a natural transformation there in one direction, but that would mean that that this thing here wouldn't be near semiring category anymore. It would be a lax. What does this one say? Yeah. It would be a lax near semiring category. But in any case, this is a big unpacked definition, but the short one is simply that the graded monad of monoids now is nothing else than a lax right near semiring functor from a given right near semiring seen as a discrete semiring category, discrete near semiring category to the category of endofunctors, which is elsewhere. Right near semiring category. And of course, you can replace the Cartesian structure with monoid, it works.
So a semiring category is one of these near right semiring objects in Kant?
Yeah. I don't know what you should call it. I mean, at least people speak about ring categories in some old literature, but actually they mean semi-ring categories then. So it's all a bit confusing, the terminology, but here I'm really up there near semi-ring. Well, yeah. So a typical example would be graded non-determinism. So suppose you want to say that the non-deterministic computation over a set is just a list over a set. So it's all the possible outcomes from a non-deterministic computation. And then a natural idea would be to say, I'm only allowed to have this many outcomes from non-deterministic computation. So the non-deterministic computation makes some binary choices, but I want to say, well, in the end, the branching is such that I only want to see max 5 outcomes, or maximum 1, or maybe opposite, at least 5 or at least 1. It's natural here to use the natural number semiring, which is of course not only a near near semi-ring, the property semi-ring. And then then you can replace the free monad by this one. So you say T of n, and x is small words or lists of length at most. Here's a cool one. So in applications, it's very difficult to check that something is a graded monad, because you really, if it's a handcrafted example, then you have to use the unpacked definition, and you've got the size of over 20 diagrams to check, and always the one that you think was the trivial one will fail, but you won't notice. So you want some systematic ways of producing graded monads. So one of those is analogous to what we have for monads. So this is distributive laws. So we would ask, what is the appropriate notion for graded monads? Well, it's a graded distributive law. Here I don't start with the motivation. I'll tell you right away what it is. So I'll first define what a matching pair of actions is between two monoids. So this is well known, I think, also from quantum group theory. So I use the name Zappa-Shed product, but people will use all sorts of other names, like I think two-sided semi-direct product and bicross product, and there are 3 or 4 more names which I've forgotten all what they are. In any case, there is this thing. So given two monoids, we call a matching pair a pair of functions like this: a south east arrow and southwest arrow. And this one here, part of the axiom say here that E1 acts on E1 as a monoid acts on E0 as a set from the left, and this one says E0 acts as a monoid on E1 as a set from the right. And the corresponding laws are here and here. But there is a bit more. There are equations that look like distributivities. So this looks as if southeast arrow distributed over times. But there is a twist, and there is a similar twist here. If you have such a thing, relating two monoids, then this gives a monoid structure on the direct product of the carriers, where the multiplication is not the one of the direct product, but it's a semi-direct product and even more. Right? So the unit is what you expect. But here you do not multiply pointwise, you use these actions to sort of distort what you would do otherwise a bit. Such monoid structures on the direct product of the carriers are called Zappa-Shed products, and there is an independent characterization of what it means to have such a thing. It basically means that you want a monoid and projections to the given monoids, and then there is a special extra condition that is called the middle unit law. So matching pair gives you a Zappa-Shed product structure, but actually the opposite is also true. So a Zappa-Shed product structure gives you a matching pair and those two are in projection. So now let's look at what happens on the monads side of the story. So we start off with two monoids with a matched pair, and then there are two graded monads. So this guy for this and this guy for this grading. And the graded distributive law is maybe what you would expect. So you want to distribute what is going to be the inner monad over the outer monad to swap them over, but you change the grades. And one way to derive the 8 laws that are difficult to remember would simply be, again, to try to write down the 4 laws governing distributive laws and see what you will be missing to even be able to write down the diagram. So here, for example, I need that this guy equals 0 and this guy equals 1. So it's a unit law and absorption law. They come from here. And 3 more equations hold, and they give 6 more conditions on matching pairs. And now, if such a thing is there, if a distributive law is there, then I can use the Zappa-Shed product to grade, well, how should I say it? I have the underlying functors here, T0 and T1. I can form their functor composition. This is just a functor, right? But I can now equip it with a monad structure and at the same time grade it with a Zappa-Shek product of the two monads I have. And this is how you do it. It's really, again, a generalization of the ordinary story about distributive laws. And you have something similar that you have in the standard result by John Beck, that there is again a bijective law between distributive laws and compatible gradient monad structures. So not only does a distributive law induce a monad structure, but it's a monad structure compatible with the given two monads in a certain way, and any such compatible monad structure actually gives you a distributive law, and this is a bijective correspondence. Let me give you some examples to justify this. This actually all makes sense from the programming point of view, and these Zappa-Shek products crop up. So I want to distribute the maybe monad, the exception monad that I showed you. Remember the one with grades pure, fail, and maybe fail? And any other old monad. So if you're in the ungraded world, this is always possible. Namely, you can always distribute a given monad over the exception monad in that direction. No, I said it the wrong way now. I can distribute the exception monad over the given monad, which means that the given monad after the exception monad is this composite functor has a monad. Now here is the graded story. So I claim that the appropriate and actually the only working matching pair for this case is this. It's defined by sort of case analysis on what the grading is for the exception. We'll have to look at these cases. So let's write down what the distributive law should have on the level, how it should look like on the level of types. Let's spell it out in all these three cases. So if I'm actually having to do with a pure computation, it is like this. So therefore you see that pure southeast arrow E0 has to be E0, and also you get one close from here. In the failure case, it's interesting because I'm describing a situation essentially when I've got some general effectful computation followed by an exception-full computation. So think, for example, nondeterminism followed by exception. You could have had a non-deterministic computation that maybe had a high grade, said 5 outcomes are possible, but now this is followed by failure. So this means you will have exactly one outcome, namely the failure. So you have to change the grade from whatever it was to the unit in the given one, here not determined. And the general case is also interesting. You cannot keep what you have, the grade for the general computation, because the thing can be a failure, or it can be a success. And depending on that, the grade should be either E0 or I0, the unit of the monoid I had for the general computation. Now I already said the unit doesn't have to be the least element in the monoid. There is nothing like this. I mean, we only require that multiplication and that addition are monotone, but there is nothing about least or greatest element. So in general, I perhaps do not even have enough structure, but suppose my monoid is an upper semilattice, I can do some small upgrading, right? So if I've got a computation that has effect E0, or alternatively a computation that has effect I0, so to unify these, I have to go up. So I use the least upper bound. So this is something that works. Let me give you another cool example, because I'm pretty close to the end. So this is a tricky one where you use the full power of Zappa-Shek products for grading. So I want to grade the stack writer monad. I'm afraid the monad itself in the ungraded form is not on the slide, but it's a simple one. So you say a computation over a value type x is nothing else than a triple of a natural number times a word times a value. So a triple of a natural number, a word, and the number, and the value. And the idea is you're saying, I'm manipulating a stack. And actually, I only write to the stack. I never care about reading, but I pop stuff from the stack, forget what they are, and I push things onto the stack. So a net effect of any stack writing computation is basically, in the end of the day, you remove some elements, some number of them, you don't know what they were, and you added some new. So it's a pair of a number and the word. So you removed maybe n many elements, and maybe you pushed, a sequence of elements that made up this word. Now imagine grading this. Perhaps I'd like to say the stack as a result of the manipulation only grows so much at most. Yeah. Then I could use the following. So So first of all, this is a composition of two monoids, obviously, where I have T0, T1, x. So this is n times sigma star x. So this is T0 is n times blank, and T1 is sigma star times blank. I could grade the first one by saying I'm removing at least so many elements. I could grade the other one by saying I'm pushing at most so many elements. So I use these guys for grading. Now, this one is a matching pair, so I use kind of a truncating subtraction. So if I subtract a greater number from a smaller number, then the result is 0. And this seems about right. So this is the multiplication that you get in the subset product. So you say this is about a sequence of computation, a sequence of stack manipulations where you first remove n0 elements, at least. Then you push n1 elements at most. Then you remove n0 prime elements at least. Then you push n1 prime elements at most. So these elements that got popped, they surely will get popped. This is reflected here. These elements that got pushed at the end, they surely get pushed. But these activities here, the first sequence of pushes and the second sequence of pops, they can cancel each other out to some degree. And this is reflected exactly by this. Oops. And here is then the distributive law. So you get the graded stack character monad by composing these two graded monads. And it's not difficult to see what you have to do. So I have to talk about this interaction of pushing the word W after popping k many elements. And I can swap these two things around. And this means I just pop less and also push less. So by vertical bar, I mean the length of a word, and drop kW just means dropping k first time. Okay. Graded comonads, how would you do that? Now you know everything, but there's nothing to say. So if you're grading by a monoid, it's if you think about it, it has to be the following thing. The graded comonad must be an oplex monoidal functor from the monoid seen as a discrete monoidal category. And that's all just fine, because just look at the kind of data that I want here. The arrows are the other way around compared to what I had before, so it has to be oplex. But of course, we do not see the full picture if I'm grading by a monoid. I should rather try to grade by a comonoid or by a general category, and then you see that there is one op missing somewhere. So, of course, it makes sense to generalize from a monoid to a partially ordered monoid, and then you see that the graded comonad is reasonably defined as an oplex monoidal functor, but not from the given comonoid, but by the opposite, from the opposite comonoid. I also had an example of a graded comonad. So this is about data flow computation. Data flow computation is computation with signals. So a stream of values is sent to a stream of values, kind of in a synchronous fashion, but you can use some memory, so that the current value in the output can depend on the current value on the input, but also on some past values of the input. And you might want to say, I can guarantee I don't need all of the history of the input, but maybe only so many last values. This is a very typical thing you want to do in actual implementation, because you don't want to have unbounded memory, but it's expensive, to say the least. So what do you use here? Normally, in the ungraded case, the comonad would simply be d of x is non-empty words over x, or non-empty list over x, where the head of the list stands for the current value, and the tail of the list stands for the past values of a given signal. But now you can grade this, so in principle I could say a computation where I know that the resource bound is n. I could say I have the current value and I have only so many values in the past. Then you can convert. So here these times must be narrow. Co-unit is identity, and delta is an interesting thing where you basically take a list of length maximum n plus m, and then morally you take the list of all of its suffixes, but you only take n first elements of that list of suffixes, and you also truncate the suffixes down to length at most n, and the arithmetic works with bounds. I won't go into this in more detail. So take away graded monads, etc. are a natural concept, both categories theoretically. So this is one of these disciplines against you have to validate all reasonable computer science. And then also reasonable in terms of programming examples, which is the other kind of criterion of truth against which you have to validate whatever you're doing. It works in both cases. So the old idea then of Waller and Tiemann of marrying monads and effects really works. But as we see, it also pays off to look at the categorical generalities to get everything right. So this concerns all these generalizations like monads of monoids. We have to use near semi-rings and the practicalities of distributive laws and the standard form of theory of monads, etc. Thank you.
We have two questions which are related. One is just to get it right. So you say the monoid has to be there. You cannot use another algebraic theory to get a meaningful notion like monad with some algebraic structure which is not a monoid.
I think the monoid is there minimally because this is there to somehow interplay with the monoid structure that the monad is.
So
but then you can have all sorts of additional algebraic structure, which I already explained in the case of for example, these near semi-rings, which are very natural for a certain type of examples. But you could go further. So for example, there are these more specialized types of nondeterminism, where the addition satisfies extra laws. So maybe the additive part of the monoid is is a band or a semi-lattice or something even more specific, and all these notions make sense. And then there is a corresponding notion of grading, where how you can grade is then accordingly limited. Because the monad has the extra structure, and then whatever you use for grading has to have the corresponding. That's my picture, but maybe there are pictures as well. But this direction works very well.
But the monoid has to be there because monads are monoids.
Exactly. Yeah. So this is what I hear always, for which I always use the multiplicative notation. So this part is always there, and then you can add useful algebraic structure.
And related to this, just quickly, I was wondering, aren't these monads in some enriched sense? Because this would give you, for instance, distributive laws more natural. You can just say these are distributive laws between these monads in a, I don't know, by category or some other enriched category. This would make somehow the theory more standard.
I don't think so. If you can tell me how.
No,
I don't see it.
That's why I
No,
asked
no,
that.
not on the top of my head.
Somehow would be nice, but yeah, I don't know.
I think it goes in a different direction.
But you see now what I mean, like.
Yeah, I see what you mean, but no, I don't see how this is working. Maybe I'm missing something.
Maybe I can answer. Probably I should write it down and pay attention, but in the very definition of creative monad, there seems to be a sort of arbitrary choice that you choose this one to be lax monoidal. Why is all lax wrong and what is strict?
Oh, wait, that's very easy. Maybe I was sloppy at this point. I'm not sloppy, but I didn't pay attention to this. So okay. So let's unpack this definition into this one, and we see where the laxness is. So
I know that I believe, but why is this direction the right one?
why is this direction the right one? Because oblax would correspond to exactly having these two arrows going in the other direction, which just is comonads. And I mean, if you have just monoidal, I mean, which some people call strong monoidal, then these would have to be isomorphisms, which also makes sense for some purposes, but not for these type of applications we have. You have something like this, right? No? I mean, you have things that are... no, it's different.
Yeah, they're usually not isos there either.
They're not isos there either, yes. At least this is... I mean, they are like monoidal functors simply for the reason that the monoid in the category of ender functors is nothing else than a lax monoidal functor and nothing else from the one-point category to the category of ender functors. So the ungraded case corresponds to when the monoid is single.
Also another one. Is there something like a graded arrow?
Yes. So you can do it in several ways. You can do arrows as I even mentioned it. So you can see arrows as monoids in prof, and you can go from there. Essentially, we say it's a lax monoidal functor from a given discrete or maybe thin monoidal category to prof functors. And similarly, you can do these lax monoidal ender functors because, or EDMs, because these are nothing else than monoids in the category of ender functors, but with a different multiplication structure, with a different tensor, which is not functor composition, but which is take convolution. And also you can see arrows as relative monads, and then it's how you break relative monads is very similar to how you break monads. So arrows would be relative monads and like that.
I think we should thank Tarmo again.
Thank you.